My name's Roger Pawlowski, and I'll be talking about the core products area. So the core products really provide our foundational capabilities, the building blocks that we build all other packages on. So it typically focuses on performant data structures, abstraction layers, utilities, and we provide a common look and feel across the Trilinos packages to try and unify things. And it also includes snapshotted packages that are developed externally, but we have copies within there that we know work with our code. So Kokkos and Kokkos-Kernels obviously are the most important ones there. So this is just the slide I copied from Kurt. I'll go through a couple of these packages and then show an example of how we might cobble these packages together into an application. And yeah, I won't talk about PyTrilinos, but Christian has a whole talk on that. So at the core of Trilinos is now Kokkos, the performance portability layer. So it's a shared memory programming model in C++, and the idea is to write your code once and run it performantly across CPUs, GPUs, or whatever's coming down the pipeline in terms of hardware. There's talks going on, obviously, if you've been here all week, you've seen tons of Kokkos talks. So I won't go into too much detail here, but the key is that they have a multi-dimensional array that has compile-time polymorphic layouts. And that's how we get performance on both CPUs and GPUs. And that is being incorporated into the C++ standard. So in C++ 23, the MD span is the equivalent of the Kokkos view pretty much. So our team works with the C++ standards committee very close. The next building block is to expand on Kokkos to support shared memory on node linear algebra, and that's Kokkos-Kernels. So it provides a portable BLAS and sparse and graph kernels. It has generic implementations, so you can do floats, doubles, complex data types. And it also will pass off, if you're using BLAS, it'll pass it off to like Rock BLAS or Ku BLAS, so it'll use the vendor optimized libraries where appropriate. But the nice thing here is they've expanded these BLAS libraries to actually hierarchic implementations. So you can call a BLAS function just using a thread block or something like that on CUDA. So that was all on node. Now what we want to do is move to MPI. We want to move to multi-node. And we add MPI parallelism through Tpetra. And so this supports parallel sparse linear algebra. So it's built on Kokkos, but it starts with these capabilities. You have a map to describe how you lay out your parallel data. And then we support sparse graphs, sparse matrices, and dense vectors and multi-vectors. And then the operations for this linear algebra, norms, matrix vector products, and things like that. We have our own MPI communication wrapper, and we can redistribute the data so you can move the data across processors using these capabilities. And then we have some nice optimizations for finite element assembly. So there's some extra pieces in there that make it really easy to assemble your matrices and vectors. So another key feature here, again, we're templated on the scalar type. So again, float, double, complex. But we also supply within Trilinos and other packages special scalar types. One is an automatic differentiation scalar type, and another is an ensemble scalar type. So you can actually pass these in and do linear algebra with those data types as well. There's really good performance monitoring. Chris is going to give a talk about that later today. The next package, once we have concrete linear algebra, parallel distributed, now we're going to wrap it in an abstraction layer. So we have an abstraction library called Thyra. Not only does it do vectors and operators, but it's also got abstractions for linear solvers, preconditioners, nonlinear solvers, and an abstraction to talk to physics codes. The idea behind this is a lot of high-level packages like nonlinear solvers, time integration, optimization, they don't care how you do the operations. They don't care what the concrete operator is. Is it Tpetra or is it something else? They just want you to do these operations. And so we kind of abstract this out, and that way, if you don't like Tpetra, you can pull in PETSI, and you can put PETSI under the Thyra abstraction layer, and a lot of these libraries will just run with those data structures. So one of the nice things, the Teuchos package, that's a physics-based block preconditioner. I'm just showing something down here. Malachi is going to talk about the Teuchos package that provides some really powerful capabilities today as well. So that was the linear algebra. Now we're going to start moving into meshing. The Zoltan and Zoltan 2 libraries, that's parallel partitioning and load balancing. So there's a collection of algorithms. There's geometric partitioning, graph, hypergraph. The original Zoltan package, it's been around since really the late 90s. That runs on standalone CPUs. Zoltan 2 was written, it's complementary. It does use Kokkos, it does use Tpetra, but it's got slightly different algorithms, and it depends on utilities within Zoltan. So it's kind of a combination package. If you enable Zoltan 2, you're going to get Zoltan 1. This will not be retired in the Tpetra retirement stack. We also have finite element I/O tools. The Kokkos library at Sandia's engineering analysis capabilities. This allows us to write finite element analysis, finite element files with all our solution data to disk in a very efficient manner. So our format is Exodus, but we do support other formats like CGNS. It goes through this IOSS subsystem layer. So Kokkos is actually split into a bunch of packages. You link the libraries against your code to write out to these different formats, but then you have a whole bunch of tools built on this. You can see the pop-out bubble up there, all kinds of tools to manipulate those finite element files. So there's a lot of nice work there. On top of that, we actually, instead of dumping to a file system, if the solution's too big, we can actually dump to a visualizer. So you can watch in real time as your codes run, you can watch the solutions as they're completed, each time step. So finally, just a utilities package. This is probably what you're going to see the most when you start to play around with different Trilinos pieces. We have a reference counted smart pointer. It's an RCP is the class name. It's the same as shared pointer, except we wrote it back in 2004 before C++11 introduced shared pointer into the standard. So most of our packages are built on that. It's interoperable with shared pointer, so you can pass them back and forth without issue. We also have a runtime database, a parameter list. This is how a lot of the packages take their input parameters when you build the objects. If you can serialize everything you store within a parameter list, you can dump it, you can read it or write it to both YAML and XML. We also have timers in here. All of the packages are instrumented with the same timer package. So you can see the output here of a timer, and it's dumping out operations coming from each of the different packages in this nested hierarchy of timers. So you can get really good timing data from your algorithms. So those are the major packages I wanted to cover, and now I just want to jump in and talk about an example application and how we've pulled it together and how a lot of teams at Sandia pull their packages together. So I'm going to talk about a project. It's called Empire, and it's modeling plasma effects in hostile nuclear environments. So the idea behind this, we use it for weapons modernization work, but we also use it to do optimization and design and to do studies within some of our large-scale reactors. So I'm just showing some of the reactors here. Z is the world's most powerful pulsed power facility. You've got Saturn, the world's brightest X-ray generator, and you've got Hermes, which is our most powerful, the world's most powerful gamma simulator. And the idea here is we put electronics and military systems into these reactors to test them. We do materials research in them as well. At the core of this, it's a relativistic particle and cell code. So we're going to be pushing particles around, and they're going to be influenced by an electromagnetic field. So we're going to solve Maxwell's equations, and we're going to use compatible discretizations to make sure we enforce the divergence constraints. We're going to solve this implicitly with continuous Galerkin finite elements along with the particle push. So the main way this works is we have a field solve. We solve the electromagnetic system. That's going to generate forces that we apply to the particles. We move the particles. The particles are going to generate currents. Those currents we're going to weight back to the electric field solve to influence how the electric field evolves, the electromagnetic field evolves. So this is what it looks like. We started Empire from the ground up based on Kokkos. So everything is designed there. We followed a component strategy. We said, if there's a component, we're going to use it. And so we actually pull in 38 Trilinos packages. We directly depend on about 21 of them. And you can see the stacks here. The next two talks by Jonathan and Morrow are going to focus on the linear solver and the discretization tools. So I won't really go into those. But we pull in all of these packages to actually build our simulation capabilities. This is more informational. I don't want to go through it too much. I already explained what the core packages do going up to here with Thyra. So we use all of these packages. One interesting thing is Empire, it's got a YAML input file. So they actually use the Teuchos parameter list to do parsing and full validation of all their input files. So they're not even using Teuchos with, well, they use it with Trilinos, but they use it separately for their own inputs. An interesting thing too is Thyra, because it's Teuchos, the blocked solvers are written to that. We actually couple to circuit simulators. We couple the PIC simulation to circuits through this blocked capability in Thyra with Teuchos that you'll hear about later. And then we use discretizations for the finite elements. The only thing I'll point out here, you heard in Kokkos, they talked about view of views and things like that. Those can be complex to implement, especially if you don't want to use UVM. So the Phalanx package has some nice performance portability tools for doing view of views, and it also has capabilities to put virtual functions on device for you. So if you need virtual functions on CUDA, that'll show you a nice implementation example. This just goes a little bit deeper into our linear solve. The electric field is in H-curl, the magnetic field is in H-div. We form this block system, and then we do an LU decomposition. We form a Schur complement. So we explicitly form and evaluate the Schur complement matrix. So we use our finite element tools, and I just kind of list them out, what packages you want to go to for the assembly, what you want to look at for data structures and for meshing. But once we generate this matrix, that's static. We update the right-hand side at each time step, and we do this linear solve. BLAS is doing it with conjugate gradient, but we precondition it with the MULU package. MULU has this very special algebraic multigrid called Ref Maxwell that's been written especially for solving Maxwell's equations. We use a Chebyshev smoother in there. And we solved this linear system. Once we solve the linear system for the electric field, then we can back solve for the magnetic field. This is on ATS2 Sierra. This is both strong and weak scaling studies. We went up to about 2,000 nodes. This machine has 4 NVIDIA V100 GPUs per node. So we're talking 8,000 GPUs, 8,000. We do an MPI process per GPU. Each of the colors on the strong scaling plot is a strong scaling study of a particular mesh. We do uniform mesh refinement to move from one color to the next. And so you can see there's a dashed line there, which is the ideal scaling. The squares are the total runtime, and you see we're not perfectly ideally scaling, but we get pretty good results. The particle push, which is the circles, that scales very well. In this case, because we spend so much time on particles, the mesh is actually fairly coarse, and so we're in a latency-bound regime with the linear solve. And so that's what you see there with the linear solve kind of being flat instead of strong scaling. But usually particles dominate a lot of our applications, and so particles are a lot higher. Now, in terms of weak scaling, again, I've got the plot of the main time, the particles, and the linear solve. You want that line to be flat because you're fixing the amount of work per process and just growing the number of nodes. So you're trying to solve a larger problem and hopefully a more accurate problem. And we do very well with the weak scaling there as well. The performance portability aspect of this allows us to jump from machine to machine to machine. So the study on the last slide is all contained here on the Sierra machine, but we were able to compare that to other large-scale platforms. Astra, that's an ARM platform, and Trinity, that's an Intel Knights Landing platform. Now the y-axes are aligned so you can compare across these plots. But you can see all of the data that we collect when we do scaling studies to look at the performance of our codes. And we do pretty well on the CPUs. We do see a better, strong scaling of a lot of these algorithms. So finally, just the most more recent is running on the AMD GPUs, the MI250X. This is just a small study, and this was just taking it, throwing it up there, and not doing any optimization at all, and comparing it to results on other machines. So we're comparing it to Cascade Lake and NVIDIA V100, and then the ARM platform again. And you can see there we're getting decent results out of the box, and we haven't even fine-tuned the linear solvers on these results. So one other thing when it comes to coupling, and I just wanted to point this out, you might run into this where you say, I've got this great application, I want to couple it to something else. Our bread and butter is a PIC simulation, but at high densities, PIC is too slow. And so we moved to a multi-species plasma simulation that uses discontinuous Galerkin fluid. We're going to couple that to our CG Maxwell discretization. But to couple it within a time step, we just typically use Picard iteration, right? Quasi-Newton, where you just solve one, transfer the data, solve the other, transfer it back. And you just iterate back and forth until you get convergence. So over a bunch of time steps, this is the number of iterations to converge that nonlinear system within the time step at different time step sizes. And you can see the iterations grow as you take larger time steps. What we did is we said this seems very unstable, very slow, so we pulled in the NOx package, the nonlinear solver package. Now it's got Anderson acceleration, which is a secant method. And because we were using the whole Trilinos, it was very easy to just turn this on, pass in the data structures, and you can see here how much we've accelerated the iterations with Anderson acceleration. In fact, the largest time step which didn't converge with quasi-Newton is now converging as well there. So I'll just finish up. This is an incomplete list of contributors. I tried to find everyone who's contributed to the core area. I'm sure I'm missing a lot. And then the Empire team as well. I just want to acknowledge all the hard work that's gone into these packages over the year. And I'll mention that most of Trilinos development is really funded out of the ASC program, NNSA's ASC program. But we also do have other funding sources here and now with Linux as well. So with that, I'll end and take questions.
Any questions? We'll probably have time for one. Thank you for the presentation. Regarding the manipulated IO package, do you handle the data at the integration points?
Yeah, we do. Yeah, it's broken up into a lot of packages, but Mauro I'm sure we'll talk about the Intrepid package, which is our finite element basis library. And so they will provide you with functions to do the integration, and you can pass your data in, but you can always take over parts of that where you want. It's very low level piecemeal, so you can do it at the granularity you care about.
Cool. Well, thank you.